Okay, so section 4.9 deals with applications to Markov chains. And it's a really wonderful section. And what I'm going to do is I'm going to let you copy this example down here, okay? And then we will discuss the solution. So let me give you a little time to copy the example down, and then we'll discuss the solution. Okay, so I know we just sort of narrate a little bit here. So what we have here is what's called a migration matrix. Migration matrix. And it's 2 by 2 matrix, and it shows the chances that a person will migrate from the city to the suburbs to the city, or from the city to the city, or the suburbs to the suburbs. So like for instance, the 0.95 here, okay, the 0.95. This means that if you live in the city, you notice the city is above the first column. The city is above the first column. So there is meant to be separation here. This is not city suburbs. This is the first column has city above it. The second column has suburbs above it. So the 0.95 means that there is a 95% chance that if you live in the city, then the next year you're going to be also in the city. You'll stay in the city. On the other hand, there is a 5% chance that if you live in the city, that you'll move to the suburbs. You see that? You see how that works? I mean, if you live in the city, you're either going to do two things. And this is a very simple migration matrix. If you live in the city, next year, you're either going to stay in the city or you're going to move to the suburbs. So if you live in the city, then next year there's a 95% chance that you'll stay in the city because you like the city, or there's a 5% chance that you'll move to the suburbs. On the other hand, if you're living in the suburbs, there's a 3% chance that you'll move to the city next year, and then there's a 97% chance that you'll move to the suburbs next year, meaning you'll stay in the suburbs. Are there any questions on, and of course, you notice that the columns add up to 1. In probability, 1 is equal to 100%, just like a decimal. 1.00 is 100%. So, you know, if you live in the city, you know, for instance, you'll either move to the city, you'll stay in the city, or you'll move to the suburbs. That's all you can do. And so the probabilities, the 0.95 and the 0.05, add up to 1. 95% and 5% adds up to 100%. Right? And are there any questions on this migration matrix? All right. Well, so initially in part A, we have let's say initially 60% of the population live in the city and 40% of the population live in the suburbs. How will the population be distributed in the region after 1 year and then after 2 years? So a question you might ask is, well, if 60% of the population live in the city, would next year the population in the city be less? This is for every year. This migration matrix is from year to year. I mean, based on the migration here, is the trend for people to move to the city from the suburbs, or is the trend from people to move to the suburbs from the city? That's right. That's right. There's a trend for people to move to the suburbs. People who live in the city, there's a trend for them to move to the suburbs. It's 5%. The trend for people who live in the suburbs to move back to the city, or move to the city, I should say, is 3%. Why do you think that is? I mean, does that kind of does that maybe make a little bit of sense? Okay, Binyam says yes. And what might be a reason why? I mean, what might be? Well, the city has a lot going on. Okay, but people who live in the city, 5% of them next year are going to move to the suburbs. People who live in the suburbs, only 3% of them is going to move to the city. So there's a trend for people to move to the suburbs overall, you know, from the city. A greater population is moving, people are moving from the city to the suburbs than the population of people moving from suburbs to the city, or I should say percentages. Okay, so Benyam says it's quieter in the suburbs. And so the one thing is having a family. That is a big, people who live in the city, you get a lot of couples who live in the city, but once they have children, they tend to some of them will move out to the suburbs because they need more space. They can't live in a tight apartment if they have a child. Well, they can, but hey, it's more comfortable for them to live in maybe a townhouse or a house. So thank you for everybody for your input. So we got a lot of questions here. Let's focus on the first question. That's another thing too, Binyam. That's another thing. Sure, that's absolutely true. The safety, I mean, with some current events, could be an issue. Could be an issue. Suburbs might be safer in certain cities. That's true. So, okay, how are we going to answer question A here? All right. So we have this initially 60% of the population live in the city, 40% live in the suburbs. How will the population be distributed in the region after 1 year? So let me go to the next page here and start off. Well, let's look at the solution here. Matthew wants to know how to work it out, and that's great. So a few things. Now, of course, sometimes I give you a guided tour of the book, right? And for this section 4.9, I'm going right to an example. But there are a few things I have to point out. First of all, that matrix M is called a stochastic matrix. And it's called that because its columns are probability vectors. Okay, in other words, the first column, the numbers add up to 1. The second column, the decimals add up to 1. And that's because they are probabilities. Okay, they are probabilities. Okay, and so the probabilities add up to 1 in each column. Stochastic methods, they do relate to probabilities. Yes, Binyam, they do. They do. And also, very good question, M is also what's called a regular matrix. It's regular because what regular means is if a matrix is regular, then you can raise the matrix to some power k, k is an integer, and you'll get only strictly positive entries. In this case, you already have positive entries. So m to the first power is the entries in all the entries in the matrix are positive. M to the first power equals m, and all those entries are positive. Sometimes you'll have, for instance, you could have a matrix like, you could have something where, you have like 0.2, 0.5, 0, and then you have maybe, 0.6, 0.2, 0.2. Got to be careful here. I need actually a 0.8 here, right? Because the columns, the numbers have to add up to 1. So in the first column, I have 0.2, 0.80. Second column, I have 0.2, 0.2, 0.2. In the third column, say I have like, 0.9, 0, and 0.1. Okay, now that matrix there, that stochastic matrix, that's a stochastic matrix here. The question is, if you raise it to a certain power, will the matrix raised to that power give you all positive entries in the matrix? Okay, and to check that, you could you could put that matrix in MATLAB and raise it to a power. You could, if this were A, say matrix A, you could just take A and raise it to like, the 5th power or something, and see if you get all positive entries. And if that didn't work, you could try the 10th power and so forth. Let me just see here. Let me just see if there's any. Well, that's what regular means. So All right, all right. So that being said, let's try to solve this problem. So what we're going to do is we're going to denote the initial population vector. We're going to denote the initial population vector denoted by x sub 0 as the 2 by 1 vector with 0.60 and 0.40. So if you remember in the matrix, the city, like moving to the city, is on the first row, moving to the suburbs is on the second row. So the 60% of people initially in the city, that goes on the first row, and the 40% of people living in the suburbs, that goes on the second row. And that's called what's called your initial state vector. It's called an initial state vector. So what do you think we're going to do with the migration matrix M and the initial state vector? What do you think we're going to do? If we want to find out, we're going to multiply them. Well, Binyam, we're not going to do AX equals B, but we're going to do multiply them as Robin said. Let me show you why. May I go to the next page? I want to make sure I'm pacing myself well. Are there any questions? All right, let me go to the next page. Thank you, Matthew. So what I have up here is just a diagram. I'm diagramming my migration matrix. This here isn't necessary, but the diagram, but it does help. I find it helpful to just give me an intuitive feel for that matrix. So you see here, the city has a arrow that returns back to the city with 0.95. Because if you live in the city, there's a 95% chance you'll stay in the city. The suburbs, if you live in the suburbs, there's a 97% chance you'll stay in the suburbs. Okay, so you're moving, you have two states, we call them states, suburbs and city and suburbs, those are your states. There's a 3% chance if you live in the suburbs that you're going to move to the city. And then if you live in the city, there's a 5% chance that next year you'll move to the suburbs. Okay, just out of curiosity, how many find this little diagram helpful? Okay, thank you, Kevin. Oh, wow, Sega, Christy, Solomon, Robin. Very nice. Thank you, everybody. It's nice to hear that. Divahan, right. Thank you, Divahar. So, okay, let's go ahead and solve the problem. After 1 year, the population distribution, which I'll denote as x sub 1, 1 year, x sub 1, that's going to be equal to the matrix, the migration matrix M, times the initial state vector x naught. And there's a reason for that, but let me just give you a moment to. Well, I'll go over it, and then I'll give you some time to copy. So what's going on here? Why does this work? Why does this work? Okay, well, so you'll notice that, what I've done is in the matrix product here, I've written out you have a 2 by 2 times a 2 by 1, so you're going to get a 2 by 1 as your product, as the product, and that makes sense because x1 is a vector. So what I've done is, using the row column method for matrix multiplication, I've written out the process here. So along the first row, you're going to have 0.95 times 0.60 plus 0.03 times 0.40. But there's more to this than just the procedure of multiplying the first row in matrix M by the column vector x sub 0. We can interpret this. We can interpret this matrix multiplication. So you see there, you have first, you have 0.95 times 0.60. Well, what that means, the interpretation of that is that, and I'll draw a little arrow here. Of the 60%, okay, of the 60% of people in the city, 95% of them stay in the city. So that means, you know, if you were to ask, hey, of the 60% of people in the city, 95% of them would stay in the city. What percent of people stay in the city? How would you find that? Well, you would take 60% and multiply it by 95%, and that's what 0.95 times 0.60 is. On the other hand, the second part, 0.03 times 0.40, okay, let's interpret that. That means that of the 40% of people in the suburbs, 3% of them move to the city. So that's what percent would that be? If 40% of people are living in the suburbs and 3% of them move to the city, we know that from the migration matrix. What percent moved out of the suburbs? Okay, so what I'm doing, all right, good questions. What I'm doing is I'm trying to help you understand that this 0.03 times 0.40 has a very common sense interpretation. It means that of the 40% of people in the suburbs, 3% of them move to the city. So what percent would that be? What's 3% of 40%? How do you take 3% of 40%? Think back to middle school when you learned about percents. That's 0.012, 1.2%. That's right, Matthew. 0.03 times 0.40. Okay, so you see the top, there's the top number. It's a 2-by-1 vector. The top number is going to tell you after a year what percent of people live in the city. Well, there's two ways that people will live in the city. They'll either be in the city and then stay in the city. That's with a certain percent. That's going to be this probability here. Or they'll live in the suburbs and move to the city, and that's going to be this second probability here. Okay, does that make sense? All right, thank you, Christy. Thank you, Robin. Is anybody uncomfortable with that? You have to let me know. There are always reasons why we do things, right? And I think that's all right. Wonderful. Thank you, Christy. Well, now let's look at the bottom row. The second row. The second row deals with what percent of people after a year are going to be living in the suburbs. Well, there's two ways that can happen. Two ways that can happen. So let me see here. Maybe I'll use gray. One way, well, no, I'll use blue. One way is that if you live in the city, you move to the suburbs. So of the 60% of people in the city, 5% of them moved to the suburbs. So that's 0.05 times 0.60. On the other hand, people who live in the suburbs, some of them will stay in the suburbs, 97%. So of the 40% of people in the suburbs, 97% of them are going to stay in the suburbs. So that's the 0.97 times 0.40 portion. And so when you do the multiplication, you're going to get 0.52, 0.582, and 0.418. That's going to be what X1 is. So therefore, after a year, 58, I mean, we started out with 60% of people living in the city, 40% of, 40% of the population living in the suburbs. And now what's happening? After a year, we have 58.2% of the population city and 41.8% of the population living in the suburbs. So what's the trend? Is the trend to that overall trend people are moving to the suburbs, or is the overall trend people are moving to the city? What's the overall trend? Well, after a year, are there less people living in the city or more people living in the city? There are less. Okay, because it went down from 60% to 58.2%, and therefore, of course, more people are living in the suburbs. Are there any questions? Any questions at all before I move on? I want to make sure everybody's comfortable before we move on to the distribution of the population after 2 years. Okay, very good. Let's go now. So basically then, after 1 year, 58.2% of people will live in the city and 41.8% of people will live in the suburbs. Now, I'm going to ask you a question here. Suppose you worked this problem out and you got 58.2% and you got 41.7%. Let's say it's on next week's exam. Okay. Let's say you got that result. Would that make sense? To have 58.2% and 41.7%. Would that make sense? Solomon says no. Why not, Solomon? Sega agrees. Well, what's the problem? Okay, Sega says 0.01 is left, and so that's right. It's not exactly 100%. You have to the percentages have to add up to 100%. The decimals have to add up to 1. Okay. Well, what you do is you go back, Matthew, and figure out where your mistake is, because it can't happen. If you're doing it right, it can't happen. Yeah. All right. And this is the lovely thing about applications. You know, when you take your exam, right, those free response questions, you have 2 tries. One try is for in case you make a typo, but the other try is to, check your answer, so you can see if your answer is reasonable with these applications. Okay, now after 2 years, the population distribution, which we'll call X2, so Binyam, precision is, that's that one, you got 2 tries. One try, you do have to be precise, of course. So now after 2 years, what's the population distribution? I'll call it X2. Well, we're going to take the migration matrix and multiply it by X1. Okay, I mean, Now that we know that the X1 is the distribution of the population after 1 year, to get the distribution of the population after 2 years, just take your migration matrix and multiply it by X1. Okay, but of course, remember, X1 equals M times X sub 0. So we could find X2 equivalently by multiplying M squared times X sub 0. And when you do that, you're going to get 0.565 and 0.435. And so after 2 years, 56.5% of the population will live in the city, and 43.5% of the population will live in the suburbs. So definitely it's trending. I mean, it has to trend that people are overall moving more to the suburbs, because the migration matrix that is telling you that based on the probabilities. All right. So let's say, for instance, you were asked, after 10 years, let's say you were asked after 10 years, what's the population distribution of people of people in the city and the suburbs? How would you do that? Okay. Yeah, you would do m to the 10th power. That you can do in MATLAB, right? And multiply it by x sub 0. Right. Okay. All right. Well, let's keep. Okay. Very good, Binyam. Binyam recalls the method. All right. Well, let's move on then. If are we comfortable? If we are, we'll move on to part B of the question. Okay. All right. So part B now says, it says, what percentage of the population will eventually live in the city? This means after a long time, will the population stabilize? Okay, will it settle? Will it stabilize? And the answer is yes. Because we have a regular stochastic matrix, there will be eventually, I mean, that you can see, like, after 1 year, after 2 years, there's migration in the population, and the percentages of people living in the city and the suburbs is changing. But eventually, the percentage of people living in the suburbs, eventually the percentage of people living in the city and the suburbs is not going to change. Okay, when the community's new, there's a lot of migration, but eventually there's going to be stability. The question is, how do we find this? How do we find this? How do we find these percentages? Okay, and here's how you do it. If there's a percentage of the population, which we're going to call Q, I'm going to call that vector Q. If there's a percentage of the population Q vector that will eventually live in the city, then the vector Q would have to satisfy this equation. M times Q would have to equal Q. M times that vector Q, which we'll call the steady state vector, will have to equal Q. And that makes sense, because what are you doing when you multiply the vector Q by the migration matrix M? Well, you're finding what's going to happen in a year's time. Well, if in a year's time the population distribution doesn't change, if it equals Q again, then you've reached a steady state. But this happens over many years, this would happen. Okay. Population, when that's what, and so the question is, how do we find that? Well, Matthew, when you multiply the vector q by m, you are finding a new population after a year. But this statement means that the population doesn't change. If m times q equals q, then the q vector has your population percentages, and you're saying they didn't change after a year. They'll asymptotically approach a final population. That's exactly right. So we got to solve for q. Well, m times q equals q. Okay. I mean, this is if this is the vector q we're looking for. Remember, this is the steady state vector. This isn't true for a vector in general, but for the steady state vector q, it is true. M times q equals q, but look what I can do on the right side. I can write the vector q as I, the identity, times q. I sub 2 times q. I mean, I can write the vector q as the identity times q. But why would I want to do that? Well, because I can then subtract iq to the left side. Okay, I can subtract it to the left side, and then I can, and I'll have that. Of course, I'll have a zero vector on the right side, and then I'll have on the left side, I'll have mq minus iq equals 0, and then I can factor out a q. Now, just out of curiosity, look how I did the factorization. Could I say that the vector q times m minus I, the identity matrix, 2 by 2 identity, does m times q also equal the 0 vector? Could I factor when I did the factoring? When I did the factoring on this step here, you notice I have the q on the right side. Could the q vector be factored on the left side? Well, let me ask you this. Let me ask you this. So your instincts are telling you no. Let me just ask you this as a question here. In matrix multiplication, in general, does A times B equal B times A? No. So, for that reason alone, this is not true. But also, you're factoring a q. You're factoring a q you have to factor it from the right side because m times q is m times q, and I times q is I times q. So the order matters because matrix multiplication is not commutative. It doesn't even matter if it's square. This is not true. The matrix factorization has to be like this. Okay, all right, very good, very good. So to find this vector q, oh my goodness, we're going to have an augmented system of equations. Here we go again. Augmented system of equations to solve. And I'll make a note here, since m is regular and stochastic, since that matrix, migration matrix M, is regular and stochastic, matrix M will have a steady state vector q by theorem 18 in your book. Okay. All right. Are there any questions before we move on to the next page here? Okay, so we want to solve this augmented matrix. Okay. So here we go. So m minus I, remember, m minus I, m, of course, is, let me just write it down. Okay, readable, readable. So M is that 2 by 2 migration matrix, and the identity is this matrix. So when you subtract the two matrices, you do it term by term. And this is why hold on here. This is why M minus the identity matrix has these 4 entries. Thank you, Christy. Thank you. I'm getting better with the mouse. That's right. I realized too, I can buy like a stylus pen. I learned that I could do that. I would prefer that. I like using the platform here. The style. But one thing at a time. I appreciate it. Thank you. Thank you, Christy. Thank you, Divahar. That's right. That's right. So, okay, so here we go. Here we go. I think, I don't think we needed MATLAB to help us here. I think we could do this by hand on the exam, right? So what did I do here? I added the first row to the second row. And put the result in the second row. Okay, and then I like to tend to have fractions. This is no big deal. I'll just multiply the first row by what? What am I multiplying the first row by? I'm taking the first row and multiplying it by 1 over negative 0.05. I'm going to need a little more room here. Taking 1 over negative 0.05, multiplying that. So, of course, I did it up here, right? Because I want a 1. I want a 1 in that first as my pivot there. So it's like multiplying by negative 20, right, on the first row. And yeah. Thank you. Thank you. Yes, everyone. That's right. So you're going to have a free variable. X2 is free. X1 is 3/5 X2. Okay, and now we're ready to solve. Now I'm going to call the vector I'm solving for here, I'm going to call it the vector x. Because this is like a general, I'm getting a general solution, and then I'll show you what q would have to be. All right, I'll move to the next page if that's all right. All right. So the vector x is going to be equal to 3/5 x2 and x2, but I'll factor out an x2, and I write that solution vector x in parametric vector form. But you see the vector q, the entries of q have to add up to 1. The entries of my steady state vector q need to add up to 1 because they're probabilities. And so, x2 is a free variable, but for this application, I have to pick x2. There's like one, it's a free variable, but it's not free, because I have to pick a specific value for x2. And I have to pick the value of x2 that'll make the entries in this vector add up to 1. So what I did here on the right, on the corner here, is I did just a little something to show you the method. So if you have a vector A with entries A, B, you want the entry, you want to convert it, you want to pick your x2. So like you multiply that matrix, that vector, by some x2. Make x2 to be 1 divided by the sum of the entries. Because if you do that, you're going to get then the vector that has first entry a over a plus b and second entry b over a plus b. And if you add these two entries, a over a plus b over b plus b, you're going to get a plus b over a plus b, which is 1. So analogously, since in my vector I have entries of 3/5 and 1, I'll let x2 be 1 over 3/5 plus 1. That's 1 over 8/5, which is 5/8, and that's going to be the value of my free variable. Pretty cool, huh? Pretty cool. So therefore, then, the vector q, the steady state vector, is going to have to be equal to 5/8 times 3/5 and 1, and that's going to get you 3/8 and 5/8. So eventually, this means then that 3/8, which is 0.375, which is a percentage is 37.5%. Eventually, 37.5% of the population in this region will live in the city. Yeah, it is cool, Binyam. I agree. In my field, mathematical statistics, there's a lot of this. There's a whole course on stochastic processes and Markov chains. It's really cool. Yeah, absolutely. Linear algebra is used a lot in statistics. Absolutely. So this means then that, should people living in this city be a little concerned? If you're opening a business in the city, would this concern you? Yes, it would. It would. Absolutely. Absolutely. So if you're gonna open up, say, a Burger King, well, should you open it in the city or in the suburbs? Well, the suburbs eventually is going to have 62.5% of people in the region. So this is like one factor to consider when you open a business. Whether you're going to put it in the city or the suburbs, you want to know how the region is going to develop over time. This is a simplified model, but you get the general idea. There are reasons why businesses open in certain areas, whether it's a city or the suburb. Well, Matthew, it could happen over 500 years. It could. So, then the question is, can we modify the model to give us some idea? Well, actually, though, hold on. If you could, I mean, the end result's 37.5%, but like, for instance, you could take m to the 10th power and multiply it by x naught, by x sub 0, and see how close you get. You could get an idea of how long. I mean, this is true. This 37.5% is like, it's theoretically where it's after many years. But maybe it's not that, but maybe you'll get close to that 37.5% after not too many years, because you're already seeing significant decline after 2 years, as Binyam says. So this is the beauty. This is graduate school. Cool stuff, right? All right. Are there any questions on that before we let's go to part C now. Let's go to part C. My field is mathematical statistics. My PhD is in mathematical statistics. That's my field, Binyam. Yep, good stuff. Applications in theory. It's a beautiful topic. Beautiful topic. So now part C says, does the eventual population distribution depend on the initial population distribution? In other words, we started out with 60% of people in the city and found that eventually, after many years, there will be 37.5% of people living in the city. But what if we started out with 80% of the population living in the city? Would that change the final result? Would that change the final result? Or if for instance, you started out with 80% of people living in the city and 20% of people living in the suburbs, eventually, after many years, would it still be that 37.5% of people live in the city and 62.5% of the people live in the suburbs? Would that result still be the same, the final result? Does the initial population distribution affect the final result? What do you think? What do your instincts tell you? Okay, so some people say yes. A lot of people are saying yes. Okay. Well, let's find out. Let's find out. Okay. Hold on. One moment. Hold on. Now, where's my? Hold on. The answer is actually no. I put a yes here, but the answer is no. I have a typo there. Well, not a typo. I got the answer, but it's not yes, it's no. Regardless of the initial population distribution, regardless, and that Matthew's right. The answer is no, and I appreciate all you smart people offering answers. And so I think it's good to offer an answer during, to share your thinking. Regardless of the initial population distribution, eventually 37.5% of the population will live in the city. 67, that should be 62.5%, not 60. Hold on, I got another typo here. This is 62.5% will live in the suburbs. So to see this, I have a little way for you to sort of see this. You could define your initial distribution vector to be just PC, PS, probability of living in the city, probability of living in the suburbs, and all the requirement is that those probabilities add up to 1. So for instance, you could have P sub C being 0.99, okay, and P sub S being 0.01. You could have anything you want. But the thing is, this steady state vector Q, the way you can think about it is, we found the steady state vector Q using the, by solving a system of equations. And like on the exam, I'll want to see that approach. But you could also think of Q intuitively as taking m to the kth power, multiplying it by the initial distribution, and letting k go to infinity. That means what would the distribution be after many, many, many years? You're letting k go to infinity. Well, if you were to take that migration matrix, and if you type that in MATLAB and you raised it to a very high power, incidentally, try it on your calculator. Try taking the matrix 0.95, 0.03, 0.05, 0.97. If you type that in your calculator and in matrix and then raise it to a high power, tell me what happens. Raise it to like the 100th power. Tell me what's going to happen. Well, actually raise it to the 1000th power. What do you get on your calculator if you raise that to the 1000th power? Maybe somebody try it and let me know what you get. So what I'm saying is take this matrix M here, put it in your calculator under matrix, and then raise it to the 1000th power. But do it on your TI calculator. That's what I'm saying. Do it on your TI 384 calculator, and what happens? So I'd like to see if just maybe one of you get a result for me. I'm sorry, I have an error here. I don't mean that. I don't, hold on. I don't mean this matrix. I mean the original matrix M. The original there's only one matrix M, the migration matrix. Take that type it in your calculator, 0.95, 0.03, 0.05, 0.97, and then raise it to the 1000th power. What happens? Well, yeah, but I don't want, so yeah, I mean, you can do it in MATLAB, but don't do it in MATLAB right now. Try it on your calculator. There's a reason I'm doing this. I want you to do it on your calculator. If maybe one or two of you could do it on your calculator, I want to see I want you to tell me what you get. So on the TI, all right, you're working on it. All right, good. I'll write down what I mean too, just so it's in the recording. Okay, I want you to raise that to the 1,000th power. And I want to see you to tell me what you get. Well, raise it, okay, but raise it to 1,000th power. I want 1,000th power. After all, okay, Christy. No, you're not doing it wrong, Christy. Okay, right, Bethlehem. You get an error, right? You get an error message. Error domain, right? Good. Then that's right, Binyam. The calculator can't handle it. Calculator cannot handle it. So you have to do it. You have to do it in MATLAB. You have to do it in MATLAB. Okay, have to do it in MATLAB. Now, let me just see here, one moment. Maybe I can bring up my MATLAB. So what I want to do is verify this here. I want to verify this 3/8, 5/8, the 3/8, 3/8, 5/8, 5/8. I want to verify that in MATLAB. Can't do it on the calculator. You can get a little bit close, but you're not going to get that exactly. That's right, Binyam. All right, so let me see here. One moment. Let me go into share application. Okay, so M equals, right? So everybody should be seeing this good. M equals 0.95, 0.03, and then semicolon 0.05, comma 0.97. Okay, and actually, let me just go to preferences here, fonts. I can make that font a little bit bigger here. There we go. All right, so take M and I'll raise it to the 1,000th power. Okay, and that MATLAB can handle it. MATLAB's good. Now, those are decimals. If we want fractions, what we can do is we can use the command format RAT. We just do, let me do a CLC. I'm going to do format RAT. And that puts it in rational format. Okay. And then M to the 1,000th power gets you 3/8, 5/8, 5/8. Well, it gets you that matrix. And you notice that both in the matrix. Well, first of all, are there any questions on that? Okay. All right. You'll notice that. Hold on. Hold on, where'd my thing go? Got to bring it back. Did everybody see the MATLAB that I did? Could you maybe just give me a thumbs up if you saw the MATLAB? I got the answer. Okay, good, good. I don't know why it disappeared, but thank you, everybody. All right, let me bring the example back here. Okay. Okay, so, you know, we're here now. This is the part we're looking at. And we've established with MATLAB, we verified it, that this is right. And you'll notice that the vectors, the column vectors, are both Q, right? The column vectors here are simply the steady state vectors repeated. Now, if we multiply that matrix by this initial distribution vector, we do the matrix math, we're going to get back 3/8 and 5/8. Because after all, the probability of being in the city and probability of being in the suburbs equals 1. So this gives you an intuitive feel for why the initial distribution didn't matter. The initial population distribution here could have been anything. Could have been anything. It could have been 0% of people living in the city. Well, it could have been 100% of people living in the city and 0% of people living in the suburbs. Okay, it doesn't matter. Okay, it's a little bit like I don't know if you remember in Calculus 2 where you did there's a problem where you do a differential equations problem where you have a briny solution coming into a vat of it comes into a tank, and then you mix it and you drain the tank, and eventually the concentration of salt in the solution stabilizes because you know it takes on the characteristic of the salt coming in. I don't know if you remember that kind of problem, but it just reminds me of that. But there you go. Are there any questions? Okay, Devahar remembers that. Yes, you must have seen that. Many of you would have seen that in Calc 2. Okay, let me stop